Hi, I'm Norman Wildberger. In this important video, I'm going to present the basics of universal hyperbolic geometry. Using only some basic ideas from ancient Greek mathematics, namely Apollonius's notion of polarity with respect to a circle, and Pappus's idea of the cross ratio, we're going to write down all of the major formulas in the subject, the really core formulas. We're going to give the main definitions of perpendicularity, quadrants, and spread, and I'm going to write down the main trigonometric laws that govern them. So this talk is meant to give you a little bit of an overview and to give us a direction to go in. Later on, we're going to come back and deal with all of these issues very carefully, slowly, with lots more examples. So I certainly don't expect you to understand completely all of the things that I'm doing now. But you will be able to see that it's relatively simple, that at the very heart of things, hyperbolic geometry is an incredibly simple and elegant subject. So, what is hyperbolic geometry for us? We're going to have 2 points of view. And these 2 points of view are going to interact as we carry on this series. The first, the more elementary point of view, the one that we're going to adopt today, is that hyperbolic geometry is the projective plane plus a circle. It's just what you get when you decide to study a single circle in the plane with projective geometry. A somewhat more sophisticated idea is that hyperbolic geometry is projective relativistic geometry. In other words, it's the geometry of Einstein's special theory of relativity as expounded by Minkowski, viewed projectively. And it will turn out that those 2 approaches are essentially the same. So special relativity and the geometry of a circle are in fact intimately connected. So this new approach is also going to be shedding light on physics, and it's going to be pointing to new directions for ways of thinking about very elementary fundamental physics. Here's 2 pictures that I want you to keep in mind. This is a picture of Euclidean geometry, and this is a picture of hyperbolic geometry. Euclidean geometry, we see that there's nothing there. It's just an empty plane. In hyperbolic geometry, we see that there's something there. There's a distinguished circle. We'll call that circle C. And we sort of imagine that that circle is given to us. We've stumbled across this circle that's God-given right there in the middle of the plane. We can't move it. We can't copy it. But we can study it. And the 2 geometries are distinguished by what tools are used to study them. The tools in Euclidean geometry are the compass and the straight edge. And also probably an area measure of some kind or another, some way of addressing area. In hyperbolic geometry, the tools are much more minimalist. There's only essentially 1 tool, and that's a straight edge. Not a ruler, so it's definitely not marked. It's just a straight edge. So hyperbolic geometry is the study of that one distinguished circle with a straight edge. That's all you're allowed. This suggests that, in fact, perhaps hyperbolic geometry is a more elementary and maybe even a more fundamental subject than Euclidean geometry. There's some case to be made for that. And so it's again not surprising that relativistic geometry ends up essentially going in this direction rather than in this direction. Okay, so what we're going to do now is we're going to study this circle with a straight edge. And the first thing that we're going to do, the first real geometrical notion that we have to develop, is the notion of perpendicularity. We have to say what we mean by perpendicular lines. Or, as it turns out, what we mean by perpendicular points. The notion of perpendicularity that we're going to introduce is different from probably anyone that you've seen before. It's a new notion of perpendicularity, so you must abandon the usual notion where this is only perpendicular. Okay? The notion here is different, but it has many similarities with the usual Euclidean notion of perpendicularity. So that's our first main notion, the notion of perpendicularity. Perpendicularity comes about via duality. And this is nothing but the pole-polar idea introduced by Apollonius. So given our circle C, every point little a has a polar line capital A, and every line big A has a pole little a. And I remind you, here's our notation for that. We say that little a is big A perp. We say that big A is little a perp. And now what we're going to do is we're going to drop this polar terminology and replace it with simply one word, duality. So we're now going to say that the dual of this point is this line, and the dual of this line is this point. Later on, we're going to study other conics as well. There will be secondary conics that appear. And when we study those secondary conics, yes, the polar terminology will be used. But with respect to our all-important null circle C, this will be called duality and not polarity. Okay, so here's a main definition. Two lines A and B are perpendicular precisely when A passes through the dual of B. And that's equivalent to B passing through the dual of A. For example, here's a line A, here's a line B. The dual of A is this point little a. The dual of the line B is this point little b. In this case, little b lies on A, and little a lies on B. Remember, that's a fundamental theorem that we have, that if A lies on the dual of B, then B lies on the dual of A. So these two statements are equivalent. And if that happens, then we're going to say that this line, capital A, and this line, capital B, are perpendicular. We're going to denote that symbolically by this symbol right here. And on the page, we're going to write a little sort of right angle indicator there, which might be slanted now a little bit because the lines aren't perpendicular in the usual sense. So in particular, if we vary this line B, but keep it going through the point little a, then it will always be perpendicular to capital A. So the lines that are perpendicular to this line here are all of these ones. All of them are perpendicular to capital A. And conversely, the lines that are perpendicular to capital B are all the lines that go through its dual, all those lines there. Now, here's the dual definition. We just had a definition about lines. Here's a corresponding definition about points. So points little a and little b are perpendicular precisely when A lies on the dual of B, which is equivalent to B lying on the dual of A. There's our symbol for two points being perpendicular. This is a notion that's not found in Euclidean geometry. It's also not found in classical hyperbolic geometry. It's just as important as the perpendicularity of lines. What's an example? Well, this same picture gives us an example also, because here's the point A. It lies on the dual of this point B, which is this line here. And so these 2 points are perpendicular. And we represent that on the diagram by putting a little right marker, just like this one here, but on the side joining A and B. That little marker there is telling us that this point and this point are perpendicular. So what are all the points that are perpendicular to A? Well, all the points on A perp are perpendicular. So this is perpendicular to that one. It's also perpendicular to this one, to this one, to this one, to this one, and so on. Now what are the points that are perpendicular to B? They're all the points that lie on the dual of B. And this illustrates a fundamental principle that's going to be very important all throughout this course. The duality principle, which says that points and lines are in complete duality. The whole theory is completely symmetrical between interchanging points and lines via this fundamental duality, A goes to A perp. So now that we know what perpendicular means, let's look at an interesting aspect of triangle geometry and ask, is it happening for us here in this hyperbolic situation? I'm interested in the question of whether the three altitudes of a triangle meet in a point. So here's a triangle, by which we mean 3 points which are not all collinear. And here are the 3 lines determined by those 3 points. So what would it mean to construct the altitude from this point to this opposite line? Well, it means we want a line that passes through this point and is perpendicular to this line. But the dual of this line is this point right here. You kind of see that via the tangent picture. It's very simple. See, that's the dual. Okay, so the altitude from this point to this line, there's only one of them, and I can draw it. There it is right there. That's going to be perpendicular. That's an altitude. Similarly, the altitude from this point to this line, in other words, which passes it and is perpendicular to it, must go through the dual of this line, which is over here. So we need a line, something like this, which passes through that point. And similarly, point there, opposite line, the dual of the opposite line, so the altitude must be in this direction. So that's perpendicular, and that's perpendicular. And lo and behold, the 3 altitudes meet in a point. This common point of the 3 altitudes will be called the orthocenter of the triangle. And somewhat reluctantly, I will agree to call this H. All right, so this point here is going to be the orthocenter of the triangle, and it'll be denoted H. We'll see later on that this plays a major role in hyperbolic triangle geometry. And it's an embarrassing fact from classical hyperbolic geometry that the corresponding fact does not hold in classical hyperbolic geometry. In the Poincare disk or the upper half plane model or even the Klein model, it's easy to construct examples where, yes, the altitudes do meet in a point, but it's also easy to construct examples where they don't meet in a point. This is an embarrassing fact which is often sort of not mentioned in courses in hyperbolic geometry. But it really takes the bottom out of triangle geometry, because if you don't have orthocenters, you don't go very far. Turns out that circumcenters also don't work in general for a similar kind of reason. But it turns out that triangle geometry is very, very beautiful in hyperbolic geometry, in universal hyperbolic geometry. And so this is going to be an important fact. We're going to talk a lot more about that later on. But already you can see some advantage in thinking about things this way, purely projectively, allowing yourself to talk not only about inside, but also outside the circle. It's in fact what classical geometers advocated about 100 years ago. Classical geometers in fact knew this fact, but they knew that you had to think outside the disk in order for it to happen. That understanding has largely, but not entirely, largely been lost in modern treatments of the subject. So now that we have perpendicularity, the next important thing to do is to measure the separation between 2 points. If we have 2 points, A1 and A2, somewhere in this plane, how are we going to measure how far apart they are? It's a fundamental thing. Now, in classical hyperbolic geometry, the answer is, well, we're going to try to introduce some kind of distance function, because it is commonly supposed that distance is the right way of thinking about measuring separation of points in geometry. Well, distance is not the right way of measuring the separation of points in geometry, as you will know very well if you've been looking at my rational trig series. It's not the right way in Euclidean geometry, as Euclid went out of his way to emphasize, but it's also not the right way in hyperbolic geometry. So our task now is to figure out, well, exactly how are we going to measure the separation between these 2 points? And the challenge for us is that we only have our straight edge. We don't have a ruler. We don't have a protractor. We only have a straight edge. Well, pretty well the only thing that we know that we can do using a straight edge to get a number is to find a cross ratio. We're going back to Pappus, again to the ancient Greeks, and taking that idea. It's got to be a cross ratio. So we have to find 4 points. Now, classical trigonometry in the Klein model also does this. They also take those 2 points and they look for 4 points by looking at the intersections of the line with the circle. Sadly, that is not the right thing to do. That is the wrong approach. Okay? That's the wrong 4 points. There is another set of 4 points which is more important, more canonical, and more general. Where are these other 2 points? The answer is we're going to use duality. Our point A1 has a dual line. Our point A2 has a dual line. Those 2 dual lines meet the line through A1, A2 in 2 new points, B1 and B2. And B1 is associated to A1 and B2 is associated to A2. Now we have 4 points. Hooray, we can use a cross ratio. We can introduce a cross ratio, and that's what we do. So here's the definition. The quadrants between the points A1 and A2 is Q of A1, A2. It's the cross ratio of A1, B2, A2, B1. The cross ratio of the 4 points A1, B2, A2, B1. There are no logs. There are no absolute values. There's nothing else. Just that cross ratio just by itself. That's the right notion of measuring separation between 2 points in hyperbolic geometry. So here's an exercise for you. Show that the quadrants between any point and itself is 0. Show that if 2 points are perpendicular, then the quadrants between them is 1. Show that if the quadrants between 2 points is 0, then either the 2 points agree or the conjugate points B1 and B2 agree. And give an example of this case occurring, where this case doesn't occur. This remark connects our notion of quadrants with the standard notion of distance in the Beltrami-Klein model, which I remind you is the model of hyperbolic geometry that you find in many textbooks, where the interior of a circle is used and the straight line segments are the geodesics, or straight lines. So if A1 and A2 happen to be inside the circle, then it turns out that the quadrants that I've defined is minus the sinh squared of the distance between the 2 points. Sinh is this hyperbolic trigonometric function, and we have to take the sinh of the distance and square it, and we have to put a minus sign in front. So all the theorems that I'm going to state involving quadrants can be interpreted in the Beltrami-Klein model by replacing quadrances with this particular expression. If you wanted to do that, but there's no real good reason to do that, in fact. It's best to stick with the universal approach. But at least this is a way of connecting our approach to hyperbolic geometry with the traditional classical one. In Euclidean geometry, the most important theorem is Pythagoras' theorem. And here in hyperbolic geometry, the most important theorem is also Pythagoras' theorem. But it has a slightly different form. Here it is. If you have 3 points, A1, A2, A3, then if A1, A3 is perpendicular to A2, A3, in other words, if this line is perpendicular to this line, then these three quadrances, Q3 is the quadrants between A1 and A2, Q2 is the quadrants between A1 and A3, and Q1 is the quadrants between A2 and A3. These three quadrances here, in this triangle, satisfy this relation. Q3 equals Q1 plus Q2 minus the product Q1 times Q2. Many of you will recognize that this is almost the same as Pythagoras' theorem in the Euclidean rational trigonometry case. If we just ignore this quadratic term, we get the classical Euclidean Pythagoras theorem in rational trigonometry language. It's a very important result. The second most important formula is the same as it is in the Euclidean case. It's the triple quad formula that concerns 3 points which are not forming a right triangle, but which are now all in a line, which are collinear. So we still have 3 points, we still have the quadrances labeled exactly the same way as before. So the quadrants from A1 to A3, that's called Q2. The quadrants from A1 to A2, we'll call that Q3. And the quadrants from A3 to A2, from here to here, that's Q1. And the theorem is the triple quad formula. If A1, A2, A3 are collinear, then this relation holds between the three quadrances. Q1 plus Q2 plus Q3 all squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared plus 4 times Q1 times Q2 times Q3. That will also be a formula that's familiar to those who have studied rational trigonometry. It's exactly the triple spread formula in rational planar trigonometry. Here it's taking the role of the triple quad formula, which in the Euclidean case is exactly the same, except it doesn't have that cubic term. So both of our two fundamental formulas are almost the same as in the Euclidean case, except that there is an additional higher term that changes it a little bit, but in a crucial way. Now that we know how to measure the separation of 2 points, we need to know how to measure the separation between 2 lines. And as Euclid knew, an angle is not the right way of thinking about this, and it leads you astray. That's true also in hyperbolic geometry, just as it's true in planar Euclidean geometry. So we're going to introduce the notion of a spread. This is also a hyperbolic version of the usual spread in rational trigonometry. And it's denoted by a capital S, not a little s as in rational trigonometry. So a capital S, the spread between 2 lines, A1 and A2. So here are our 2 lines. There's A1 and there's A2. And they meet somewhere. And we want to define the spread between these 2 lines. And this is a number that's associated to the 2 lines. Not rays, but just the lines themselves. We're going to do exactly the same thing as we did when defining the quadrants between 2 points. We're going to use duality. This line A1 has a dual point, namely little a1. This line A2 has a dual point, namely little a2. We can draw the lines from this intersection through A1 and through A2, giving us 2 new lines, B1 and B2. But now we have 4 lines, which are all concurrent at the same point. And so we have a cross ratio. Actually, we have a number of cross ratios, but we're going to pick the right one. And here's our definition. The spread between lines A1 and A2 is capital S of A1, A2. It's the cross ratio of the four lines A1, B2, A2, B1. It's exactly the same expression as with the quadrants, except there's capitals here instead of little ones. So it's the cross ratio between, there's A1, B2, A2, and B1. And the relative positions of these four lines can change depending on where they intersect and where they're positioned with respect to the circle. Okay, now the duality between points and lines extends to a duality between quadrants and spreads. And here's a very important theorem again. They're all important theorems. The quadrant spread duality theorem says that if little a1 is the dual of the line capital A1 and little a2 is the dual of the line capital A2, then the quadrants between little a1 and little a2, between those two dual points, is the same as the spread between the two lines that we started with. So quadrants and spread are not different kinds of measurements. They're in some sense really almost the same, except that quadrants is measuring separation between points, spread is measuring separation between lines. So how does this notion of spread between two lines connect with the notion of an angle between two lines in the Beltrami-Klein model? And the answer is that the spread between the two lines A1 and A2 is the square of the sine of the angle between the two lines. Well, we shouldn't say the angle, we might say an angle, because there are a number of different angles, but you take the sine and square it, you get the same number. So again, we can connect with the traditional formulas. So that means that you can take any one of the formulas that I'm presenting here or later on in the course, replace the spreads and the quadrants with sine squareds and minus sinh squareds. And if the corresponding points or lines are sort of happening inside the circle, then you recover a formula from classical hyperbolic trigonometry. Another point is that in rational trigonometry in the plane, the spread between two lines is always in the interval 0 to 1. But here in hyperbolic geometry, the spread can in fact take on any value. It can take on negative values and values bigger than 1, and even infinity in certain special cases. And let's just reiterate again that in hyperbolic geometry, the quadrants Q and the spread S are really dual concepts. This is an extension of the duality principle, so not only are lines and points in a dual relation, but also quadrants and spread are in a dual relation. It means that whenever we have a theorem involving quadrants and spreads, we can dualize things to get a new theorem. Well, it's usually a new theorem. Sometimes it's actually the same as the original theorem. So here's a good example of that idea of dualizing a theorem. This is Pythagoras' dual theorem. Now we have three lines. Line A1, line A2, line A3. And we're going to suppose that A1, A3 is perpendicular to A2, A3. That's a little bit less familiar of an idea. So A1, A3 is an intersection. It's that intersection right there. And A2, A3 is the intersection right there. So we're assuming that this point and this point are perpendicular. Points can be perpendicular, remember, just as well as lines can. And that little symbol there is telling us that these 2 points are perpendicular. And by the way, that means that if you take the dual of this point, you get a line on which this point lies. Or conversely, if you take the dual of this point, you get a line on which this point lies. So if these things are perpendicular points, then there's a relationship between these three spreads formed by the three lines. And it is S3 equals S1 plus S2 minus the product S1 times S2. And similarly, there's a kind of dual version of the triple quad formula, the triple spread formula, which concerns three lines, A1, A2, A3, which are concurrent. So if the lines are concurrent, then the three spreads that are made, here's our notation, the spread between A1 and A3 is S2, spread between A2 and A3 is S1, and the spread between A2 and A1 is S3. Let me just make sure you all appreciate that these two lines, A1 and A3, for example, the spread between them is denoted by this little symbol right here, but it could just as well have been placed between here and here, or between here and here, or between here and here. We are talking about lines, not rays. The spread is something measuring the separation between those two lines. Okay, so in this kind of situation, when we have three concurrent lines, then the three spreads satisfy, well, it's the same formula, except it has spreads. S1 plus S2 plus S3 squared equals 2 times S1 squared plus S2 squared plus S3 squared plus 4 times S1, S2, S3. And now let's write down the main formulas for a triangle that involve both quadrances and spreads. So here is a triangle. A1, A2, A3 are its vertices or points. And we have various quadrances. There's Q1 between here and here, Q2 between here and here, Q3 between here and here. And we have the spread S1 here between these two lines, spread S2 here, and the spread S3 here. So we have these 6 quantities. We want to know what is the relationships between them. And there are essentially sort of 2 laws. There's the spread law, which is the analog of the sine law in ordinary trigonometry, which says that S1 over Q1 equals S2 over Q2 equals S3 over Q3. So the ratio between this number and this quadrant is the same as the ratio between this number and this quadrant, and the ratio between this quadrant and this quadrant. So students of rational trigonometry will recognize that's the same spread law as for quadrants and spreads in the Euclidean context. The cross law is the most complicated of these laws. It's also, in some sense, the most powerful one. And it takes some getting used to the power and the beauty of this formula. It's a little bit intimidating. Let's have a look at it. It's a formula that involves 3 quadrances and one of the spreads, S3. It's only appearing there. It's a quadratic equation for S3 in terms of the other 3 quadrances. And it says Q1 times Q2 times S3 minus the sum Q1 plus Q2 plus Q3 plus 2. All of that squared is 4 times 1 minus Q1 times 1 minus Q2 times 1 minus Q3. And that's actually just one of 3 cross laws. We could sort of rotate the indices around. There's a corresponding law where there's a 2 here instead of a 3, and there's a 1 where there's a 1 there instead of a 3. And there's exactly a dual law here where the quadrances are replaced by spreads and conversely. And it's exactly the same form, but it's S1, S2, Q3 minus and so on. So those are the main formulas for universal hyperbolic geometry. They're going to be the basis on which we investigate a wide variety of things. They are also amongst the most important formulas in mathematics. They are certainly within the top 20 formulas in mathematics, in my opinion. Pythagoras' one is certainly in the top 10, probably the top 5. We're going to have to go very carefully over things again. We're going to develop these formulas. I want to lay them out here for you. So that, first of all, this is a reference. So you can come back and watch it and remind yourself of what the basic framework is and how we're really only relying on the notion of duality, which comes from the ancient Greeks, the notion of cross ratio, which comes from the ancient Greeks. Otherwise, we're doing things which I hope you will at some point appreciate is almost obvious. We're just doing kind of obvious things and asking obvious questions, and these are the formulas that we obtain. So, a big exercise. Okay? Try to verify all, or at least some, of these theorems. Make some diagrams. Make some diagrams with perpendicularities if it's Pythagoras. Make some computations of quadrances and spreads. Remember, you can measure a cross ratio. Just take a ruler, measure some separations or displacements, divide one displacement by another, divide another displacement by another, take the ratio. That's a cross ratio. So it's not too hard to calculate quadrances and spreads directly from a diagram. And you can verify that these formulas, at least within the accuracy of your drawings, sound reasonable. And you can also experiment to see what happens when the points are in various positions. They take on different kinds of values if the points are inside or outside, or some of them are inside or some of them are outside. These formulas all hold no matter where the points are, subject to a few special cases. Sometimes when we're talking about null points or null lines, we have to interpret our formulas in a different way, or maybe they're not valid in those cases. There's some infinities that are appearing. Alright, so that's a lot of material. It's meant to be an overview. I don't expect you to all understand it right away. Slowly, as the course progresses, you will understand the significance of these formulas more and more. I hope you grow to appreciate them and really like them. Next time, we're going to start introducing some coordinates into the picture. We want ultimately to prove these formulas, to derive them. And we need some kind of coordinate framework to make computations. And we're going to start off with the simplest framework, which is just simple Cartesian coordinates, and we're going to talk about the circle in Cartesian coordinates. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.